Ahoy, you filthy swines! Welcome to what the bloody oink is going on. And let's read some stuff. There's a case a few years ago of a star being discovered that appears to disappear or fade at unpredictable intervals. And some people were saying perhaps that star might actually have some kind of alien megastructure around it. And the name, I think, most commonly used to describe these structures is a Dyson Sphere. But anyway, this article on Scientific American, written by Kimberly Cartier and Jason T. Wright, have aliens built huge structures around Boyajian's star? I don't know. Should we find out? Alien technology is probably not causing Boyajian's star to dim mysteriously, but alternative explanations are hard to come by. One quiet afternoon in the fall of 2014, just as the trees were changing from green to gold, Tabitha Boyajian visited our astronomy department at Pennsylvania State University to share an unusual discovery. That landscape on the brink of transformation turned out to be a fitting backdrop for a meeting that would change the course of our careers. Then, a postdoctoral scholar at Yale University, Boyajian had flagged inexplicable fluctuations of light from a star monitored by NASA's planet-hunting Kepler Space Telescope. The fluctuations looked nothing like those caused by a planet passing between the star and the telescope. She had already ruled out other culprits, including glitches in Kepler's hardware, and she was looking for new ideas. One of us, Wright, suggested something very unorthodox. Perhaps the fluctuations in brightness were caused by alien technology. In the 1960s, physicist Freeman Dyson postulated that advanced energy-hungry civilizations might enshroud their home stars in solar collectors, later called Dyson Spheres, to absorb practically all of the star's light. Could this fading star be the first evidence that other cosmic cultures were more than science fiction? That outre idea was a hypothesis of last resort. I know these scientists, they don't like to entertain the idea that perhaps there are creative forces in the universe. When they come across that, they end up throwing derogatory comments like God of the Gaps and other accusations of zaniness, which is unfortunate. Which is why I'm kind of inclined to go down these paths, because somebody has to. And if somebody doesn't take them seriously, then we may miss out on the opportunity to spot something that is very obvious out there. And everybody's covering it up because they refuse to acknowledge that something strange could be going on. Let's find out, shall we? But for the time being, we could not dismiss it. The star that stumped Boyajian, now officially known as Boyajian's star and colloquially called Tabby star, has captivated astronomers and the general public alike. As with all great enigmas, it has generated a seemingly infinite number of possible solutions, none of which wholly explain the curious observations. Whatever is responsible may lie outside the realm of known astronomical phenomena. Before Kepler's launch in 2009, most planet hunters doggedly revealed new exoplanets, planets orbiting other stars one by one, like anglers pulling individual fish from the sea. Kepler came along like a trawler, scooping up new worlds thousands at a time. For 4 years, the telescope community observed stars in one small patch of the Milky Way. It was looking for planetary transits in which fortuitously aligned worlds cross the face of their host stars and block a fraction of the starlight seen from Earth. Graphed over time, the brightness of a star is described by so-called light curve. With no transiting planets, the curve will resemble a flat line. Add in a transiting planet, and that light curve will now include U-shaped dips that recur like clockwork each time the orbiting body blocks the star's light. The duration, timing, and depth of the dips convey information about the planet itself, such as its size and temperature. Of the more than 150,000 stars Kepler surveyed, just one, dubbed KIC 8462852, that's very catchy, after its number in the Kepler input catalogue, displayed a light curve that defied explanation. Members of the Planet Hunters Citizen Science Project were the first to notice it when they scoured Kepler's data for transiting worlds overlooked by professional astronomers' automated planet hunting algorithms. KIC 8462852 showed transit-like dips in starlight seemingly at random, with some lasting a few hours and others persisting for days or weeks. Sometimes the star's light dimmed by about 1%, characteristic of the largest transiting exoplanets, but other times it plummeted by up to 20%. No conceivable planetary system could produce such an extreme and variable light curve. Perplexed, these citizen scientists notified Boyajian, a member of the team overseeing the Planet Hunters project. In 2016, they introduced the star and its mysteries to the world in a peer-reviewed journal article with the subtitle, "Where's the Flux?" Boyajian's star held yet more surprises. In the aftermath of the WTF, where's the flux? WTF. Oh, I'm slow on the uptake there. Astronomer Bradley Schaefer of Louisiana State University claimed, based on archival data, that Boyajian's star had dimmed by more than 15% over the past century. So we'd had that star tracked for a while then. The claim was controversial because such multi-decadal dimming seems next to impossible. Stars stay at nearly the same brightness for billions of years after they are born and only undergo rapid changes just before they die. These rapid changes take place in the timescale of millions, or rather billions of years, and are accompanied by clear markers that Boyajian's star lacks. According to every other measurement made, it is an unremarkable middle-aged star. There is no evidence that it is a variable star, pulsing with a regular beat, and there is no indication that it is accreting material from a companion star. No suggestion of anomalous magnetic activity, and no reason to think it might be young and still forming, or phenomenon that could rapidly alter its brightness. In fact, aside from its anomalous dimming, this star appears entirely ordinary. Enigmatic light patterns to astronomers, there is usually no mystery behind a star fading in the sky. Star spots, as well as the shadows of planets or debris disks, routinely dim the otherwise steady light from mature stars, but none of these exoplanets seem to apply for one mercurial middle-aged sun known as KIC 8462852, also called Boyajian's star. Why don't you just call it that for now? Just call it that. Typical light curve. A dimming star can be studied by its light curve, its brightness plotted over time. A planet or disk transiting across a star causes a dip in the curve. For planets, this dip recurs every orbital period. Star spots create patterns in light curves based on a star's rotation rate and activity cycle. Not so typical Boyajian star, the light curve of Boyajian's star is widely variable. Some dips last for days and others persist for months. Some scarcely dim the star's light, and others reduce it by 20%. Beside these dips, Boyajian's star also is steadily dimming and may have darkened by more than 15% during the past century. Transiting planets, debris, disks, and star spots cannot explain these phenomena, leading astronomers to look for exotic solutions, including the idea that the star's light is blocked by swarms of satellites built by an advanced alien civilization. And also, considering it dimmed by 15% on average in the last 100 or so years, could suggest that they've been constructing this thing in real time over this period, and actually, that's what we're seeing there. Yet Schaefer's claim held up when astronomers Benjamin T. Montet and Joshua D. Simon checked it with the original, lesser-known Kepler calibration data. They found that Boyajian's star faded by 3% over the 4-year Kepler mission, an effect as extraordinary as the shorter-term dips. We must now explain two mind-boggling phenomena related to Boyajian's star: slow dimming over the last 4 years, and possibly the past century, and deep, irregular dips spanning days or weeks. Although astronomers would prefer a single explanation for both, each phenomenon is difficult to explain on its own and even harder to explain when considered in tandem with the other. Here, we consider some of the most oft-proposed scenarios to explain the bizarre observations of Boyajian's star. We will judge each on how well it explains the observations and offer our subjective assessment of the probability that the theory is correct. A disk of dust and gas. The irregular dips and long-term dimming of Boyajian's star are seen elsewhere, around very young stars with still forming planets. Such stars are belted with circumstellar disks of starlight warmed gas and dust that, as they form planets, develop clumps, rings, and warps. In disks seen edge on, these features can briefly dim a star's light, and wobbling circumstellar disks can block increasing amounts of star's light over decades and centuries. The star is middle-aged, not young, and apparently devoid of a disk. That disk would, as with anything warm, radiate heat as extra infrared radiation, yet Boyajian's star shows no such excess. It could be that the dust and gas exist in a very thin ring sprawled wide around the star, so that the rim blocks starlight along our line of sight without producing much infrared excess. Such rings have never been observed around a middle-aged star such as Boyajian's, because this scenario can explain Boyajian's star only by invoking a never-before-seen phenomenon. We judge it to be very unlikely. Well, also, Dyson Sphere is a never-before-seen phenomenon, so is this less likely than a Dyson Sphere or more? I don't know. It would have to be dead on, wouldn't it? And very thin, with lumpy clumps, maybe. I don't know, like Saturn, but, you know, it's a star, isn't it? It's not small like Saturn or Jupiter. A swarm of comets. Boyajian's original hypothesis was that transiting swarms of giant comets caused the star's dimming. Comets, after all, spend most of their time far from their star and have highly eccentric orbits, which could account for the irregularity of dimming. But what about the lack of heat? The comets would certainly warm up as they approach Boyajian's star and quickly lose that heat as they departed. Any infrared excess would therefore be detectable only during a dip. We detect no infrared excess now, but that absence would make sense if the comets that caused dips a few years ago are now very far from the star, cold and giving off no detectable heat. Even so, any cometary swarm that could also cause the mysterious long-term dimming would have to be very large, unavoidably creating an infrared excess, which, as noted, is missing. So it's not that then. Thus, our verdict is that a cometary explanation is plausible for the dips and very unlikely for the long-term dimming. It stands to reason, though, that if the comets are not causing a long-term dimming, then they are probably not causing dips either. I don't think that sounds likely. I mean, you're effectively saying instead of there being a disk around the entire sun, that it's clumps of planetesimals and comets and stuff all swarming together. Okay. But it dips in intensity fairly frequently, doesn't it? So whatever is transiting across, it wouldn't just be one swarm of comets. It would have to be periods of different swarms of comets, which itself is weird. Is that not weird? It seems weird. A cloud in the interstellar medium or solar system. Interstellar space is strewn with gas and dust that diminishes starlight. Maybe an intervening cloud or dense sheet of this material blocks a shifting fraction of light as Kepler's line of sight passes through different parts of it during the telescope's orbit around the sun. Such a cloud could have a density gradient that dims Boyajian's star over long timescales, as well as small knots of material that could cause the extreme short-term dips. So are we suggesting this is something that isn't orbiting Boyajian's star, but is somewhere between our solar system and somewhere nearer to home? This hypothesis finds some support in the work of Valery Makarov of the US Naval Observatory and his colleague Alexei Goldin. They argue that some of the smaller dips of light attributed to Boyajian's star are actually deep dips in brightness from fainter adjacent stars in Kepler's field of view, possibly caused by swarms of tiny dense clouds or comets in interstellar space. We subjectively rank this hypothesis to be plausible, but only happening in the line of sight between here and there. I mean, is that plausible? Maybe, I don't know. A related hypothesis suggests that the obscuring cloud could be at the outskirts of our own solar system. In that case, Kepler's orbit around the Sun would take the craft's line of sight through such a cloud every year, but we see no annual repetition to the dips of Boyajian's star. Furthermore, there is currently no reason to think that such a cloud exists, although one could conceive of a cloud of ice and vapor arising from geysers on a Pluto-like body much further out from our sun. Until planetary scientists weigh in on this hypothesis, we rate it conceivable but unlikely. And also, that dwarf planet would itself be orbiting the sun, so wouldn't stay in a fixed position, would it? Intrinsic stellar variations. Stars do change in brightness when they begin to exhaust the fuel supply in their core. But this happens on timescales of millions of years, not centuries or days. And at the end, not the middle of a star's life. Naturally occurring phenomena such as a star's spots and flares, seen often on our own sun, change the brightness of stars on shorter timescales. We may not need to invoke additional orbiting material if the irregular dips and long-term dimming can be explained by brightness variations innate to physical processes within Boyajian's star. Recently, Mohammed Sheikh and his colleagues at the University of Illinois at Urbana campaign statistically analyzed the timings, depths, and durations of the short-term dips, finding that they are distributed across according to a power law, characteristic of a continuous phase transition, such as magnets realigning themselves in the presence of an external magnetic field. They suggest this distribution could hint that the dips of Boyajian's star are caused by it being on the cusp of an internal transition, such as a global flip of its magnetic field. But no star like Boyajian has ever displayed such activity. In fact, the star appears too hot to have the type of stellar dynamo that generates magnetic effects within cooler stars such as our Sun. Most problematically, stellar magnetic fields could not create long-term dimming we see. Columbia University astronomer Brian Metzger and his colleagues there and at the University of California, Berkeley, have fleshed out a more feasible explanation in which a planet or brown dwarf collided with Boyajian's star. The collision would cause the star to temporarily brighten, and the long-term dimming we see would be the star returning to normal brightness. This scenario does not naturally explain the irregular dips or the detailed shape of the dimming seen by Montet and Simon in the Kepler calibration data, but future studies could solve these problems. For these reasons, we render a verdict of somewhat plausible for the merger scenario and very unlikely for other explanations invoking intrinsic brightness variations. Black holes? One common idea suggested by the public is that a stellar mass black hole in close orbit around Boyajian's star could block the star's light. That hypothesis fails, however, in three ways. First, because such a black hole would tug the star to and fro in the sky, it would create an easily detectable wobble, a wobble that Boyajian's team looked for and did not detect. Second, stellar mass black holes are far smaller in size than stars, so one of them would block only a minuscule amount of the star's light. But would there be lensing? Would it be diffracting the light or anything? In fact, a black hole's intense gravitational field would counterintuitively magnify most of the background star's light rather than blocking it. Exactly, lensing. Third, when a black hole consumes gas and dust, it heats the infalling material so much that it glows brightly in all wavelengths. If there really were a black hole between us and Boyajian's star, we would expect a brightening, not dimming, which we definitely do not see. So no black hole, right? Well, not quite. A possible solution involves a distant free-floating black hole drifting between Boyajian's star and us. Imagine that such a black hole is orbited by a wide, cold disk of material, like the rings of Saturn but larger than our entire solar system, and that this disk possesses an almost transparent outer region and a dense inner region. Such a disk could cause the long-term dimming of Boyajian's star as its nearly invisible outer region, followed by its dense inner region drifting across our line of sight during the past 100 years. The star's irregular dips might then be shadows cast by rings, gaps, and other substructures in the transiting disk. Such a black hole and its hypothetical disk would have escaped Boyajian's efforts at high-resolution imaging because it would emit no light itself. Because we lack observational evidence that black holes host cold, sprawling disks at all, this scenario may seem a bit far-fetched. But theorists predict that such disks as a byproduct of the supernova that gave birth to stellar mass black holes. Moreover, statistical estimates do suggest that such a black hole could have passed in front of at least one of the 150,000 stars monitored by Kepler during the 4 years of its survey. We subjectively rate this theory as somewhat plausible. Your ratings, they're not very clear. Somewhere, I mean, stick your finger in the air. It kind of could have happened, yeah. Alien megastructures. I was wondering also, aside from alien megastructures, I remember as a companion to a black hole, some people in the past had theorized about white holes, and I wonder whether it would be easy to detect the difference between a star and a white hole being the exit point of a black hole. I don't know if this is even remotely plausible anymore, considered plausible. But if there is a black hole somewhere with a wormhole linking to an exit point, a white hole, could there be matter falling into a black hole somewhere else in the universe and spewing out of a white hole? And you have misidentified Baojian as a star when in fact it is a white hole just vomiting out energy from matter falling into a black hole elsewhere. And the variability is based upon the variability of the matter falling into the black hole. I don't know. Is that plausible? I rate that as ruddy amazing. There we go. That's my idea. Anyway, alien megastructures, also a pretty massively amazing idea. Let's go with this one. Having examined a host of natural explanations for the odd behavior of Baojian's star and found them lacking, we can now consider the most sensational possibility: an alien megastructure, akin to what Dyson described more than half a century ago. Imagine that an alien civilization built large numbers of energy collection panels and that the panels had a range of sizes and orbits around the star. The combined effect of the smaller panels of the swarm would be that they blocked some fraction of light from the star, like a translucent screen. As denser parts of the swarm come into and out of our line of sight, we might see variations in brightness on scales from hours to centuries. As first noted more than a decade ago by astronomer Luck F.A. Arnold, particularly large panels or groups of panels flying in formation, even bigger perhaps than the star itself, would cause huge discrete dips to their geometric shape as they transited. As with the circumstellar disk hypothesis, the lack of infrared emissions is a problem. Even alien megastructures must obey fundamental physics, so any energy from the starlight they intercept must ultimately be radiated away as heat. This requirement holds no matter how efficient their technology is. Well, we don't know that. We don't know the limits of technology, though, do we? Energy cannot be destroyed, so if they are collecting a lot, they must also get rid of a lot in the long run. I remember reading a novel by David Brin called Sundiver. It's the first novel in the Uplift saga, which is a great series of novels. And in that, they created probes to go into the sun to explore the sun. And they used refrigeration lasers to cool the craft. I think refrigeration lasers are a real thing. So even though these things may warm up, maybe they're beaming energy away from them, which is then cooling them. So I don't know. Is that something that's plausible? So they may not be giving off infrared because they're actually cooling themselves by purposefully radiating with refrigeration lasers. Does that make sense? There are still ways to make the hypothesis work. A megastructure swarm might radiate as it gathered energy away as radio or laser signals instead of heat. That's exactly what I said, sir. It might not form a spherical swarm, but a ring precisely aligned with our line of sight. It might use technology beyond our understanding of physics that emits no heat at all. You just said you couldn't do that, but now you said you could. Because of the myriad of unknowns, this hypothesis is very hard to test. Okay? The alien megastructure hypothesis would have to be considered seriously if all natural hypotheses are ruled out. Alternatively, it would find support if we detected obviously artificial radio signals being transmitted from the vicinity of Baojian's star. A search we have already begun with Baojian using the Green Bank telescope in West Virginia. For now, our verdict on the most sensational hypothesis to explain Baojian is that its plausibility is unclear. We just do not know enough to put even a qualitative probability on the actions of a hypothetical alien life. So you're not even going to posit a basic explanation there. An unknown bright future. Where does this leave us in trying to understand Baojian's star? We can rule out any explanation that requires an excess of infrared energy because it's not observed. We can also reject scenarios that require many low probability events or that invoke physics or objects we have never seen before, at least until all other options have been eliminated. Because you didn't even consider white holes. Are they too outdated now? Do we not consider those anymore? Wormholes? No? The best path forward is more fact-finding. Baojian, now an assistant professor at Louisiana State University, leveraged the public fascination with this star into a successful crowdfunding campaign that purchased time for us on the Las Cumbres Observatory Global Telescope Network. On May 20th, 2017, this additional monitoring paid off when the star's brightness once again started dipping, this time down to almost 3% below its usual brightness. Astronomers around the world volunteered labor and telescope time to monitor the star across the electromagnetic spectrum, giving us access to spectral information we lacked during the dips observed by the Kepler mission. We are hopeful these data will help us rule out some of the scenarios here and perhaps generate new hypotheses to explain them. Other astronomers are seeking out additional archival measurements of the star's brightness to learn more about its long-term dimming. Knowing the timescale of the dimming would further constrain theories about the star's odd light curve and improve our knowledge of how to search for more observational clues. We also await a better measurement of the distance to Baojian's star, due from the European Space Agency's Gaia mission, which should help eliminate some hypotheses. If the star is closer than 1,300 light-years, extinction from gas and dust in the interstellar medium cannot explain the current level of dimming. If instead the distance is about 1,500 light-years, the current best estimate, the long-term dimming could perhaps be because of chance patterns of intervening dust along the line of sight. But if the star is much farther away than that, it is far more luminous than previously believed, and then the dimming could be a return to normalcy after a merger, as Metzger's team has suggested. Unless and until more information trickles in, our speculations about Baojian's star are limited only by our imagination and a healthy dose of physics. Like the best puzzles in nature, the journey to the truth behind this enigmatic star is far from over. Well, it's well written, sir and madam. Great discovery of a mystery. And the illustration at the top, I think, is quite interesting. Is this the proposed example of what it might look like? Maybe. It also reminds me slightly of Ian M. Banks. He wrote a whole series of novels about the culture, which was effectively, if you imagine the Western world taken into the far future with hypercapitalism and giant orbital habitats. Maybe these are giant orbital habitats that are floating around this star, not just solar collectors. Maybe. I don't know. Maybe they are the result of some kind of runaway nanotechnology or a von Neumann machine that is just building multiple copies of itself. Who knows? But it appears to be stumping all these brainiacs. I also like the idea of a white hole. I want to know if that's a bad idea. Are white holes a thing anymore? That could be a thing. Who knows? Maybe that is a discovery waiting for something like Baojian's star. Maybe it's not a star. Maybe it's the exit point of a black hole. Maybe we've been misdiagnosing some stars or some white holes as stars, you know. But that is it for now. Make sure you hit the like button if you like me. Subscribe if you like me long time. But for now, the only thing I have left to say is Pigwig out.
Oink, oinkity, snort, snuffle, snuffle, squee, oink, oink, ree, squeal, snort, snort, oinkity, squee. Oink, 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 squee, squee, ree, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 ree, 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 oh. Snort, snuffle, oink, squee, squeal, ree, snort. Oinkity, oinkity, oink, oink, snuffle, ree, squee, snort, oink, squeal. Oink, 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 squee, squee, ree, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 ree, 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 oh. Oink, oinkity, snort, snuffle, snuffle, squee, oinkity, oink, oink, snuffle, ree, squee, snort, oink, squeal. Oink, 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 squee, squee, ree, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 ree, 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 oh. Squeal, squeal. Snort, snuffle, oink, ree, squeal, ree, snort, oinky, oinkity, oink, 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 snuffle, ree, squee, snort, oink, squeal, oink, oink, oinkity, squee, squee, ree, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 ree, 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 oh. Squeal, squeal, snort, snuffle, oink.